guys, so I am going to do notes today on the properties of matter, including water. You can find this in chapter 2 of your textbook. And I will end by talking about enzymes, which is a special type of protein. Remember, we talked about proteins with macromolecules earlier in this unit. So, properties of matter, including water. So let's start by talking about the atom, which I'm sure you remembered from elementary school, and then again in middle school you probably learned about it. So we know that the atom is the smallest basic unit of matter. If you have a lot of atoms of the same type, you call that an element. Okay, and we know, carbon, hydrogen, oxygen, we've talked about all of these so far this unit. This is the periodic table. You do not need to know how to use this in biology, but this is, you've seen this before. This is the table that shows you all of the different elements in our world. So, if you go on to take chemistry next year, then you will learn how to use this and, go much more into detail with all the different types of atoms and what makes them different from one another. But for our purposes, you just need to know the basics of the atom and the elements. So parts of an atom. There's a nucleus, that's the very center. The nucleus is made up of protons, which have a positive charge, P for positive, P for proton, and a neutron, which is actually neutral, which means it has no charge, zero. It's neutral. It's neither here nor there. It is not positive or negative. It really just adds weight to the atom. So that's the nucleus. And then around the nucleus are these teeny tiny little units called electrons, and they orbit them. So very similar to, how planets orbit the sun. The sun would be the nucleus and the planets would be the electrons. These are negatively charged. Electrons have a negative charge. They surround the nucleus in energy levels. The nucleus is super tiny. It is so small, and atoms are actually primarily empty space. So, thinking about our solar system, and you have the sun in the middle and planets surrounding it, we are like millions and millions and millions, the Earth is millions and millions and millions of miles away from the sun. That is very similar to how an atom is oriented. So you have the nucleus, and this picture shows that the electrons are really close together, but they're actually not. There is so much space in between. Just kind of, I don't know, I think it's kind of interesting. So an atom is, again, the nucleus made up of protons, which are positively charged, and the neutrons, which are neutral. Neutron sounds like neutral in the nucleus. And then the electrons are all around the outside, very, very far from the center, but make up are negatively charged and surround it. So a compound are different elements that are bonded together. So, we've been talking about this for a while now. Maybe you didn't know we were talking about compounds, but we were. So water is the most common compound that we will talk about, and we have been talking about in biology. You get that from adding an oxygen and 2 hydrogen atoms together. So that is a compound. Carbon dioxide is another one we've talked about. Carbon, CO2, so you've got 2 oxygen and 1 carbon. That is a compound. And when you have different atoms added together to create a compound, it takes on new properties than the individual element together. So if you think about it like oxygen just by itself, or hydrogen just by itself, they are floating around all around us right now. They're gases. If you take hydrogen and oxygen and put them together, most commonly found on Earth is water. You get a different form. So it's an example of how adding atoms or adding elements together can give you a compound that has a much different property than if they were separated. So compounds, as they're added together, and something has to cause these two different atoms to stick together, and these are called bonds. So there's a few different types of bonds. The first type that we'll talk about is called a covalent bond. So when two atoms share electrons, they become covalently bonded. And a covalent bond also means that they are sharing their electrons equally. So we'll see in a little bit how electrons cannot be shared equally, and that's a different type of bond. But covalent bond, you have two atoms share electrons, and that is what bonds them together. So let's look at something that is that you guys already know of, which is sucrose. So sucrose, that is one of the macromolecules we talked about, carbohydrate, and sucrose is actually the combination of two smaller little carbon rings, glucose and fructose. But when we were looking at these, what's important to know is that this is showing carbon atoms. So this is showing covalent bonds of two carbon atoms. So over here we would see just one carbon atom binding with another one because they're sharing two electrons. And when they're sharing those two electrons, it just helps bring them in a little bit closer together. So over here with this diagram, what we have is a ring, and basically this is just a different diagram that shows carbon atoms that are sharing electrons with one another to create this stable structure of, let's see, 1, 2, 3, 4, 5 carbon atoms right here, and then right here we've got 1, 2, 3, 4. So let me draw. What we have at each one of these little where these two lines meet, that's supposed to represent a carbon atom. Carbon. This is an oxygen atom, so anything that's not explicitly said is supposed to be a carbon. So carbon is binding with this carbon. Carbon's binding with this one. Also binding with the hydrogen and the oxygen. Okay, so that's how these different rings can form. So carbon is sharing electrons. These are all covalent bonds because they are sharing them equally with one another. Carbon normally creates covalent bonds. Not always, but normally does. So we already talked about how not all atoms share electrons equally. Some atoms are better at attracting the electrons, so the electrons spend more time by that atom. So what you can think of is like some elements or some atoms are more greedy with and have a greater pull on electrons than others do. So we call these polar molecules. Polar molecules. Big one that we mentioned and we talked about with this unit is water. Water is a huge polar molecule. Well, it's not huge, but water is a very important polar molecule, and because of its polarity, that's why we get all the different, that's why it's so important for our planet and for living things, and it's also why it acts the way that it does and all the different properties that it has. So electrons are not being shared evenly between two atoms, and the electrons are spending more time near one atom and less time near the other atom. So if we have this example up here in this little picture, it's a polar covalent bond. So covalent means, they're sharing electrons. Polar means one of them is hogging the electrons more away from the other one. So it's spending more time with that. So with this, it would be Cl, which is chlorine, I believe. It is hogging the electron from hydrogen a little bit more. So hydrogen is still sharing that electron with it, but it's more polar. So what that means is if the electrons are going to be more on this side of this atom, it's going to have slightly more of a negative charge. And that's because electrons have a negative charge. So if one atom is, trying to hog and pulling the electrons a little bit more towards it, usually it's because that atom is bigger. Chlorine is a much bigger and heavier atom than hydrogen is. Hydrogen is so teeny, teeny, tiny. It's the smallest type of atom that you could get. Chlorine is pretty big and hefty and has more like gravity and more ability to pull electrons towards it. So because of that, it's going to have more of a negative charge. And hydrogen will have more of a positive charge. Because of this discrepancy in charges, it's not even. So and one side is a little bit more negative than the other and one's a little bit more positive. That is what we call bipolarity. It's polar, meaning it's not going to be even and neutral all the way through. It will be a little bit negative on one side of the compound and a little bit positive on the other side. So that's what this describes down here, this part. The molecule develops slightly charged regions. This would be the negatively charged region. This would be the positively charged region with HCl. There's a slight negative charge on the atom where the electron spends more time. And there's a slight positive charge on the atom where the electron spends less time. So water is polar. Let's diagram water real quick. Water is a very, very polar molecule. And let's just draw a little bit of it right now. So we have water molecule, which is 2 hydrogen atoms. So this would be a little hydrogen atom. This would be a little hydrogen atom. And so H2O, and then oxygen is the larger one. Oxygen is a much larger atom than hydrogen. We already talked about how hydrogen is the smallest, teeniest, tiniest element in our world. Oxygen is pretty big, and usually we draw oxygen as red because guess what? It becomes more negatively charged. It likes to hog all those electrons and becomes a little bit more negatively charged. Okay, so we've got oxygen atom right there, and I'll just draw the 2 hydrogen atoms as black for H2O. And then we have hydrogen, hydrogen. Okay, and these are going to be slightly positive because again, oxygen likes to hog the electrons away from hydrogen. Hydrogen is still sharing; they're still sharing the electrons, but like I said, oxygen is a little bit bigger and it has a greater pull. It's a heavier molecule. It's going to pull hydrogen a little bit more and have more of those electrons near it. So this is water. Usually, you know, it's drawn like this. You might see it flipped the other way, where I think it looks kind of like Mickey Mouse. You've got hydrogen, hydrogen, and oxygen. Looks like Mickey Mouse. So hydrogen bonds, they occur in some polar molecules. They occur in water, and hydrogen bonding is why water is so amazing and why it has so many crazy different properties, which we'll look at in a little bit. So water forms hydrogen bonds. The hydrogen in water forms a weak bond with an oxygen atom in another water molecule. So let's diagram that. We had, let's actually go back to what we had back here. So right, we had these two. We had this molecule and this molecule. Because oxygen has a slightly negative charge up here and hydrogen has a slightly positive charge, if you have a lot of them all together, then they're going to start to orient themselves a certain way. So let's draw that. Okay, so if we were to draw that, let's draw a few of them. So we have oxygen, right, negative, 2 hydrogens, hydrogen, both positive. Okay, if we had a lot of them, oxygen, hydrogen, so that's negative and positive, oxygen, 2 hydrogen, negative, positive. You could see that this oxygen atom is negatively charged and the hydrogen is positively charged because again, it's a polar molecule. They're not the charge, the negative and positive charge, it's not neutral throughout the whole thing. There's one side that's negative and one side that's positive. And what do we know? Think about your magnets. You have one side that's positively charged, one side that's negatively charged, and opposites attract. You have a magnet, they are going to attract to one another if you have one negative and one positive side. So there's going to be a little bit of attraction right here between the oxygen negative and that positive. So remember, opposites attract. Okay, positive is going to love negative. And these are going to repel each other. So H over here and this positive is going to repel each other, but this negative up here and this positive is going to attract one another. So on this next page, where we just were, this really shows that. So, you know, again, inside of the atom itself, between the oxygen and the hydrogen, that's what we call a covalent bond, and more technically, we would call that actually a polar covalent bond because there's unequal sharing of the electrons. These little dotted lines right here represent hydrogen bonding because, again, we said the oxygen atom was negatively charged and the hydrogen atom was positively charged. So it's not an actual bond. It's not like they're actually sharing electrons, and because that would be a covalent bond. What it's showing it's kind of like a magnet. When you get a little close to, when you hold a magnet a little close to another magnet or to the fridge, you know, and you feel that connection, but it hasn't actually like stuck yet. That's what we call hydrogen bonding, is they're not actually going to, boom, stick together, but they will like each other and hang out next to one another because that's negative and that's positive. Okay, so again, dotted line shows hydrogen bonding between two different molecules. This is one molecule by itself, this is one molecule by itself, and they orient themselves this way. Okay, then we have other atoms, or I'm sorry, other type of bonding that is called nonpolar molecules, and they don't have any charged regions, so this is another type of covalent bond, but again, it's nonpolar, and that's equal, completely equal sharing of electrons throughout it. That's kind of what we talked about up here with when we just first introduced covalent bondings. I said that there is an equal sharing between them of electrons, and you know, just to be more specific, we would say that that is nonpolar. Just means that there is equal sharing. See, look how happy they are. So H2, hydrogen and hydrogen sharing two, you know, or binding together, they would be sharing equal electrons. So there's no positive side, no negative side, it's just equal all the way through. Oil is very nonpolar. A lot of gases are nonpolar, you know, nitrogen, oxygen, things like that. All right. This is one of the reasons why oil and water don't mix, because we have oil is nonpolar. It's nonpolar, and what did we just spend 5 minutes talking about? Water is polar. And when you mix polar and nonpolar, you can't mix them at all. So if you mix water and oil, they don't like each other. That's why oil is going to stick up by itself, because it doesn't care about the hydrogen, or it doesn't care about the water and its polarity, and the water is all going to, you know, be binding with itself through hydrogen bonding, or hydrogen bonding, yeah. All right, so properties of water. It's all about the H2O, and it's really all about the hydrogen bonding for the most part. So let's do a quick review. Polar molecules have a slight charge. Because they do not share their electrons equally. Okay, so one side's going to be slightly positive, one side's going to be slightly negative. H2O is a great example of that. Nonpolar molecules do not have a charge because they share their electrons equally. Water is an example of a polar molecule, and it forms hydrogen bonds again, because our oxygen atom is slightly, slightly negatively charged, slightly positive charged, so they kind of start to orient themselves this way, as a little upside down or right side up. Mickey Mouses, but basically the oxygen atom and the hydrogen atoms like to get together because there is just a slight little bond between them, because one's negative and one is positive. All right, this is just what we talked about. Remember, water is a polar molecule and it forms hydrogen bonds. It's these little dots right here, hydrogen bonds. It's not an actual bond, just because they kind of like each other. They're negatively charged and positively charged. This is just a fancy chemistry signifier, symbol that shows positive and negative charge. All right, so we're going to talk about high specific heat of water, cohesion and surface tension, and adhesion. So hydrogen bonds cause 3 properties of water: high specific heat, cohesion, surface tension, and adhesion. All right, high specific heat. So high specific heat is the first one. This just means it's the energy required to raise the temperature of something to 1 degree Celsius. So water has a very high specific heat. It takes a whole lot of energy just to increase the temperature of water 1 degree Celsius. And that's because you have to break those hydrogen bonds. So, breaking those hydrogen bonds, that's what helps. Like when water gets really, really, really hot, what does it start to do? It starts to boil. And then finally it, if a hydrogen bond breaks and it's at the surface, then water can escape into the heat or into the air as water vapor, so it can evaporate. So again, why? It's because you have to break those hydrogen bonds. And water, those hydrogen bonds, they don't seem like they're very strong, but they're very, very strong. That's why water takes so long to heat up. Think about if you're cooking, during the pandemic lately, everybody's been spending a lot more time at home and been cooking a little bit more. So hopefully you've at least experienced boiling water sometime in the past couple months. In my house, we like to eat a lot of Italian food. We like to cook a lot of pasta, a lot of rice. You have to boil water for both of those. So when you're cooking pasta or you're boiling water, you get your pot, put water in it, you start boiling it. What gets hot what gets hot quicker? Is it the pot or is it the water? It's definitely the pot, okay? You're gonna have that sucker on for, 10 minutes, 15 minutes before the pot is getting so hot before the water actually starts to boil. It takes forever. If you salt it, that actually, that's kind of something different, but salt ends up breaking some of those hydrogen bonds so it can more quickly, so it can kind of heat it up faster. Or if you're at the beach, think about when you go outside, when you're at the beach, does the sand get hotter faster or the ocean? Definitely the sand. You can be on the sand, burning your feet, you walk into the water, and it is freezing. All right, hydrogen bonding also has to deal with cohesion and surface tension. So this basically means water likes to stick to itself. So cohesion is the attraction between water molecules. Okay, it likes to stick to itself. So if you were to put a lot of drops on a penny, you can get something that looks like this, and it doesn't really spill out because the water is sticking to itself and creating this kind of bubble. Surface tension, it's how difficult it is to break that surface, and water has a very high surface tension as well. So cohesion, hydrogen bonding keep water molecules together, and it makes them hard to break apart. This is how you get animals that can actually walk on water. Little gliders or little lizards that can just move really, really fast. Usually they have, feet and that are very webbed or very spread out and small so that they can take all the advantage of that high surface tension of water. Adhesion is water liking to stick to other surfaces. So depending on the type of surface, water will stick to it or it won't. So that's why one of the reasons why, waxy coatings on leaves or on feathers is so beneficial for, the survival or for insulation. Think about like water or, ducks that live in the water, very cold places. They need waxy coating so that water doesn't get in there and then get them wet and cold. So if you have a surface that is nonpolar, like lipids, or like a waxy coating, water's not going to want to stick to it. But most other surfaces, water will stick to it. So like a paper towel, right? You just stick it right one little corner in there and water will just creep up because it is sticking to something that it likes, like temperature, or like this paper towel. All right. Water is also considered the universal solvent. Universal solvent, because it dissolves almost everything that you put into it. Okay, so solvent would be this, all of the whatever is dissolving it, and the solute is in it. Another way to remember this is, I like to draw this. You draw solvent really big, and then the V really, really big, like a adult beverage glass. Solvent, right? Looks kind of like a martini glass. I didn't say that. And what do you put into it? You put solute into the solvent. So use, it's supposed to be little u's. Solute goes into the solvent. Common solute and solvents would be what we were just talking about with boiling water and salt. So salt would be the solute. And what do you put it into? You put it into a pot of water, which is then the solvent. That's why water is considered the universal solvent. It will dissolve pretty much anything that you put into it. Sugar, salt, soap. Well, not really. Soap's a bad example because it's kind of polar. But you get the idea. Okay, so which of these colors represents the solvent or the solute? These little Mickey Mouse guys, those are definitely water, and we know that water is the universal solvent, so that's going to be the solvent. And our big green and orange guys are going to be the solute. You put a solute into the solvent.